Today I will be discussing Lab 2, looking at the motion of a falling object. In this lab we were tasked with capturing the motion of an object falling from rest. The purpose of this lab was to look at the motion of this falling object and determine the forces acting on the object. The results of the experiment show that gravity is not the only force acting on the object. There is also a force due to drag or wind resistance. The motion of the object can be modeled using Newton's second law. We're going to use it in the same way as we did for the first lab, where final velocity equals initial velocity plus the net force divided by the mass times change in time. We are also using the position formula again, which is defined as final position equals initial position plus velocity times change in time. Looking at the video and tracker, we can see that the ball moves in the negative y direction dropped from rest. The position versus time graph shows that the slope, which is the velocity, is not constant. This means that there is some force acting on the object. To create a model of the ball's motion, we must first set initial conditions. We set the ball's mass equal to 0.057 kilograms, the ball's initial position to the vector 0, 0, 0, or the origin, and the ball's initial velocity to negative 1.4 in the y direction. Our other initial conditions are the time step, or delta t, the force of gravity, which is 9.8, and the direction of gravity, which we are going to use as j hat. Using the initial conditions that we just mentioned, we can now create an equation for net force. Weight, which is the ball's mass times the force of gravity times the direction vector, or j hat, is equal to the force of gravity, which we are assuming is the only force acting on the object. You can also see where Newton's second law and the position equation are entered into our while loop. Now, if I run our code, we can see that the ball moves in the negative y direction with one force acting on it, which is the force of gravity. Comparing this model to our experimental data, we can see that the model overpredicts the change in velocity. This is due to the fact that there is another force acting on our object, which is the drag. To account for drag, we must include the force due to drag in our equation for net force. The force due to drag is equal to b, some constant, times the magnitude of the ball's velocity squared times our position vector j hat. B is defined as the proportionality constant, which is used to find the magnitude of the drag force. Running our new code, we can see that there is now a force acting opposite to the force of gravity, which is the drag force. If we plot these results with our experimental data and our model with no drag, we can see that the blue line, the model with drag, is much closer to our experimental data. This means that it predicts the motion of our ball much more effectively. Terminal velocity occurs where the drag force of a falling object and the force due to gravity on the object are equal. So the change in velocity of the object falling is 0. Due to the fact that our first model had no force opposing the force due to gravity, it will never achieve terminal velocity. Our second model, however, will. If we change the time interval to allow the code to run for additional time, we can see that the drag force, the blue arrow, will grow until it is equal to the yellow arrow, which is the force due to gravity. If we look at the graph, the slope of this line, which is the change in velocity, becomes constant. This means that the force due to drag and the force due to gravity are equal, meaning that there is no change in velocity. If the object was initially thrown downward, it would move towards terminal velocity through an opposite reaction. the drag force would be greater than the force of gravity, and it would decrease until they were equal. In conclusion, the motion of a falling object is always affected by some force due to drag. This is shown in the discrepancy of our first model, which did not account for drag, and then the better fit for the second model, which did account for drag. The object can also reach constant velocity when drag force and the force due to gravity are equal, meaning it has achieved terminal velocity.